Dr. Saurav Chakrabarty, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today we will be doing divide and conquer algorithm, and using that same technique of divide and conquer, we will be looking at algorithms for finding the minimum and finding the minimum distance in a line. Till now, we have seen various kinds of algorithms. We have seen the naive set of algorithms, where we go through the whole list of input or whatever object that has been given as input, and we solve it accordingly. Or we have seen the recursive algorithms, where we have cleverly used the recursive algorithms to call the same function again and again. And the third one that we have seen was usage of data structures for getting some good algorithms. For example, in the case of heap sort, we saw that how to use data structure like heap can be helpful for getting a good algorithm in both in terms of time complexity as well as in space complexity. So, in this talk and in the next few lectures, we will be looking at various kinds of algorithms. So, in general, the algorithms has been split into 3 or 4 different categories. So, the most commonly used things are divide and conquer algorithm, the greedy algorithm, and the dynamic programming algorithm. In this lecture, we will be doing greedy algorithm, and in subsequent lectures, we will be looking at greedy algorithm and dynamic programming algorithm. So, just to inform you guys that this classification of algorithms is nothing that is written on stone. It is just some kind of a marker to help us understand or categorize the algorithms into various sections. So, there are many problems that can be called as greedy algorithm, and someone might call it as divide and conquer algorithm, and so on. So, although we will categorize it in 3 different classes, and each of them will have its own technique in some sense, but there is no reason to believe that an algorithm has a very right classification. These are the 3 techniques for algorithms, and which technique is useful for solving which problem is something that is completely unknown and as such. So, it all depends upon the solver or you to come up with the right model of algorithm or right concept of algorithm to solve the problem. There can be more complicated problems which can use this algorithms in a very complicated fashion, like the part of it can be greedy, part of it can be divide and conquer, and so on and so forth. Anyway, so we will see some divide and conquer algorithm. So, before that we have to understand what do we mean by a divide and conquer algorithm. So, this is the same kind of concept that was used by various administrators or kings earlier in the history. So, the idea is just to divide this problem into small problems, and if you divide these problems into small problems, then possibly solving the small problems is easy, and you can solve it using recursive calls to that algorithm. And then once you have recursively solved the small problems, then we appropriately combine their answers. So, we have seen this kind of algorithm already in our last few lectures. For example, the first algorithm that we saw was this GCD, which was a recursive call to itself, and it is not very clear whether this can be called as a divide and conquer algorithm, but at least it is a recursive algorithm. So, every time the algorithm is called on a smaller input, and so you are basically breaking down the original input to smaller and smaller inputs where we are solving it recursively. Binary search, that was clearly a divide and conquer algorithm. We are looking for a particular element in a sorted list, and what we did was that we went to the middle element and we asked either this element is in the first half of the input or in the second half of the input, and which one to go or which one to search is something that is determined by whether the element that we are searching is smaller or greater than the middle element. Quick sort and merge sort were two classic examples of divide and conquer, where we have the set of numbers that we want to sort. We just split it up into two sets of smaller size, and then we sort them recursively on each of the smaller inputs, and then finally we combine them together in some nice way. In the case of quick sort, there was no concept of combining, because we just had to put these two lists one after another. In the case of merge sort, we had to merge it carefully. So, this technique of divide and conquer can be applied to various other problems. In the next two lectures, we will be looking at very complicated algorithms for which uses divide and conquer approach. So, in today's lecture, we will be doing some more basic problems. So, let us start with the simple problem of finding the minimum. So, basically we have been given a set n containing n numbers, set S containing n numbers, and we want to output the minimum number in that set S. This is a problem that we of course face in a very day to day life, and because many times we have these sets of say set of winners or sets of smarts, and we want to find out the highest scorer or the lowest scorer or so on. So, what can be an approach to solving this problem? So, we have been given n numbers and we want to find the minimum. So, here is the first attempt that we can think of. First attempt is simple. We sort the numbers in an ascending order. Now that we have a very good understanding of sorting of a list of numbers, we can use our favorite algorithm, say merge sort or heap sort or whatever, and we sort the numbers in S in an ascending order. Once we sort the numbers in S in an ascending order, then all we need to do is output the first element, because note that the first element then will be the minimum in that set. So, this algorithm is simple, and it is of course the first attempt that one can think of. So, what is the time complexity of this algorithm, or the run time of this algorithm? We know that sorting this set of numbers in an ascending order takes order n log n, and of course, finding this first number from the sorted list takes order 1. So, in total this attempt will take order n log n. Now, can we obtain this thing in order n steps or something? Let us see. So, this brings us to the divide and conquer approach. So, in the attempt 2, what we do first is that we will split this problem into smaller problems and solve it there. So, let us see. The idea is just to split this set S into two equal sets of size S1 and S2 of n over 2 each. Then recursively we find the minimum in the set S1 and the minimum in the set S2, and we output the minimum of these two minimums. Note that this will indeed output the minimum of the whole set, because minimum of the whole set will be minimum over all the elements in the set S, which is the minimum of the minimum in the set S1 and the minimum of the set S2, which we get as recursive calls to that set S1 and S2. So, this is also not a very complicated algorithm as such, except that we have to understand the runtime. The runtime is a bit tricky for any form of divide and conquer algorithms. We have seen some examples of that in our quicksort algorithm or in our binary search algorithm or even in our finding GCD or merge sort. So, the idea is basically to define T n to be the number of steps required for finding the minimum in a set of n elements, which is in this case, or in general define T n to be the number of steps required to solve that problem. And now, since you have split that whole problem into two smaller or multiple smaller problems, so you can use that set of recursive calls to obtain a recurrence relations on T n. For example, here note that if T n is the number of steps required to find the minimum in a set of n inputs, what did we do? We split it up into two sets of size n over 2. For each of these sets, finding the minimum would have taken T of n over 2, because that is what we have assumed by the definition of T n. So, we have this say T n over 2, one of them is being used for finding the minimum of the first half and the other one is being used for the minimum of the second half. So, we have twice of this, and what do we do finally? We will just output the minimum of those two, whatever we answer we get, and thus we have the plus 1. So, now that we have got this kind of a recurrence, and we can also get some obtained like what is the value in the case of T of 1. Now, this is a very crucial thing, that we need to stop somewhere and we need to understand how it will behave when in the base case or in when the sets of size is 1 or so on. So, in this case we can say that if the set is of size 1, then the minimum is itself. So, it will just output it without even looking at it. So, T of 1 we can say is 0. So, under this condition T of n is twice T n over 2 plus 1. So, if you expand this T of n over 2, this will come to T of n over 2 is equals to twice T n over 4 plus 1, and we multiply it with by 2. So, we get 4 times T n over 4 plus 1 plus 2, and once we see this kind of a recurrence, we try to imagine what is the value of T of n is, and T of n is comes to 2 to the power k T of n over 2 to the power k plus 1 plus 2 plus so on till 2 to the power k minus 1. And note that this long sequence of numbers is a geometric sum, and so we get T of n is equals to 2 to the power k times T of n by 2 to the power k plus 2 to the power k minus 1. Now, if you put k equals to log n, then we get 2 to the power k will become n. So, this becomes T of 1 which is 0, and so basically we get T of n equals to n times T of 1 plus n plus 1. In other case we get T of n equals to n minus 1. So, thus we have that while a naive algorithm for solving the minimum takes order n log n steps, a divide and conquer approach will take order n steps. A natural question to ask will be that can someone use this approach to get say the fifth smallest in this set S? That is a very interesting question, and we will answer that only in the next lecture. We will take a short break now. When we come back, we will look at another simple algorithm which will use divide and conquer algorithm. Welcome back after the break. Before the break, we saw the algorithm for finding the minimum in a set of n elements, and we saw that divide and conquer approach can help us to obtain an order n upper bound. One small question that one might want to ask is this tight? And I leave it to you guys to decide whether one can obtain a better upper bound than order n. So, a better algorithm that takes less than order n steps to find the minimum in a set of size n. So, now let us move on to a new problem. So, this problem is about finding the minimum distance in a set. So, again we have been given a set of n elements or n numbers, and we want to output the minimum value of I minus j, where both I and j are in S. So, thus we want to find out the closest two numbers in S. Note that the S is not sorted. So, S can be anything, and finding the minimum is somewhat minimum distance between these two can be somewhat hard. For example, if this is S, say a set of numbers randomly chosen, and if I ask you what is the minimum distance, you will take a few minutes to decide what is the minimum distance. So, what is the output? Just by looking at it, one cannot say. We have to come up with a more cleverer algorithm. So, let us see what one can do. So, here is the first attempt that one can make, very similar to the case of finding the minimum in a set of n elements. Here also one thing that we can do is that we can consider all pairs I and j in S. Now, for all pairs I and j in S, I will store the value of I minus j, the value of I minus j in a set T, and finally, we will output the minimum value that we get for T. Now, this algorithm again is obviously correct, because we are going over all possible I j combinations or I j pairs, and for each of the I j pair we are noting down the difference between I and j, and then among the set of all of them we are outputting the minimum. Note that if we have a set of n elements, the total number of I j pairs that can be possible are order n square, rather exactly n square, we write it as order n square. And to find the minimum value from the set of n square, we just now saw that one can come up with an algorithm that takes order n square steps. So, this basically gives us that the total runtime for finding the minimum distance in a set of n elements takes order n square running time. Question is, can one do better? Again we have to go back to our divide and conquer approach, which will help us to do better. So, what is the idea? The idea is, first of all, sort this set S in an ascending order. Then we split this set S into two equal halves, and we somehow solve it recursively for each of these halves, and then we combine it carefully. So, let us see it by an example. So, say here is this problem and here is the set S. So, what is the first thing we do? First step is we sort this set S. So, when you sort this set S, so we get something like this. Now, not only that, we also split this set S into two equal halves. So, we will color the first half of them red and color the next half of them blue, and we split this set S into two equal halves. So, we get S, which is the smallest n over 2 elements, and S 2, which is the largest n over 2 elements. Let us see. If I have I j pair in S which achieves this minimum distance among all the set of pairs in S, then what all the possible things can happen? The first thing that can happen is that both I and j are in S 1, the first half. The second thing that can happen is both I and j are in the second set S 2. And the third thing is, while one of them is in S 1, the other one is in S 2. Here I assume that I is in S1 and j is in S2, it does not matter exactly which way you do, because anyways I and j can be anything. So, once we have split this set S into these two sets S1 and S2, we have three conditions that can happen. Either I and j are in the both in S1, or I and j in both S2, or I is in S1 and j is in S2. Now, we solve the problem recursively on the set S1 and S2. Now, in other words, we find out the minimum distance among pairs when both the pairs are in S1, and we also find the minimum distance among in pairs when both the pair is in S2. So, thus say the minimum distance in S1 S2 is 3. So, this kind of takes care of these first two conditions when I and j are both in S1 or I and j in both in S2. But what happens if I is in S1 and j is in S2? Note that if I is in S1 and j is in S2, then I and j are minimum when I is the maximum in the set S1 and j is the minimum in the set S2. This is because S was a sorted list and S1 contained the lowest half or the smallest half of the elements in S, and S2 contained the largest half of elements in S. So, if say I was this and j was this, that could not have happened, because then I know that the next element is clearly bigger than this element, and so this 55 minus 35 must be smaller than 55 minus 31. And similarly, I know that 37 is less than 55. So, it is a clear observation that the minimum can happen only when I take the maximum in the set S1 and the minimum in the set S2. And after we are done with that, so we find out that in this case I minus j, or in other words I minus j, if you want to take a mod, we can take a mod, is 2. So, and what do we output? We see that if I and j are in S1, then the minimum distance is 3. If I and j are in S2, then the minimum distance is 3, and if I and j are one in one set and the other in other set, then the minimum distance is 2. So, this gives us the algorithm for solving the minimum distance. Now, what is the pseudocode of this algorithm? It is a step by step process. We first sort it, we put the smallest n over 2 elements in S1, we put the rest, or which is the largest n over 2 elements in S2, we find the k1, which is the minimum of S2 minus maximum of S1. So, what is this? This is the third condition that we had, where I is in S1 and j is in S2. Then we find k2 by recursively calling the same function minimum underscore ds dist in S1, and k3 by calling minimum underscore dist in S2, and we output the minimum of these 3. The correctness of this algorithm is not hard to prove, and I will skip that one. It kind of follows in the same argument that I gave while doing the example. What we want to check is the runtime of this algorithm. Now, again, like in the case of any other divide and conquer approach, let Tn be the time taken to find the minimum distance of elements in a set of size n. So, note that in that case the sorting takes order n log n steps. Now, once we have sorted it, putting this smallest elements n over 2 elements in S1 takes order n steps, and putting the rest in the S2 takes order n steps. Finding the minimum in S2 again takes order n steps, finding the maximum takes n steps. So, finding the difference will take order n steps, and finding the minimum distance by the recursive call will take t of size of S1, and similarly in the case of minimum distance in S2, so will t of size of S2. Finally, we take the minimum of these 3, which is just as one single step. So, in other words, we have order n, order n, order n, we have order log n, and t of S1, t of S2, and order 1. So, we have t of S is something like order n log n plus order 1 plus t of S1 plus t of S2. since size of S1 is n over 2 floor of that and size of S2 is n over 2 ceiling of that. So, we have T of n is order n log n plus. Note that order n, we can always assume that order n is equals to order n log n, because n log n is greater than order n, and therefore, we can combine these two to write order n log n. If you recollect, in the asymptotic notations, we do not care about the constants, and so we can just combine two functions which just differ by a constant amount easily. So, now that we have this recurrence relation, how do we solve it? Solving certain recurrence relations can actually be very tricky. So, once we have this T of n is order n log n plus T of n over 2 plus T of n over 2, we will write T of n as is something that is less than some constant times C times n log n, some constant which we do not know. And then we will prove that T of n is constant n times log n whole square, and we prove this using induction on n. Now, this step one has to be a bit careful here, because one has to use induction to solve it, and more importantly, how do we get this value is something that one needs to work hard on. I will not go into details of this particular case of how to solve this recurrence relation, but one can show that by induction T of n is constant times less than or equal to constant n times log n whole square. So, T of n is order of n log n whole square. So, to summarize, we had a naive algorithm that took order n squared steps, and then we used the divide and conquer approach to take order n log n whole squared steps. The question is that can one improve this one to order n log n steps? The answer is yes, one can improve, and I will leave it for you guys to think about it. In the next lecture, we will be talking about a very similar problem, and then we will see how to use some slightly more trick to improve the runtime from order n log square n to n log n. By the way, this problem of finding the minimum is also called finding the minimum in a plane. The reason is that one can think of this problem as one giving a straight line which is the x axis, and all the points S, the numbers are numbers on this plane, and what we want to find out is, so number plane number on the line, and so what we want to find out is the closest distance between two such points in this line. So, this problem is also called the finding the minimum distance on a line. Okay, to summarize, so we have the divide and conquer approach. So, we have already seen this approach earlier, but today we saw the application of it is even more to finding the minimum in a set of n elements, and then finding the minimum distance in a line. In the next lecture, we will see much more interesting applications of divide and conquer approach. Thank you.